In biology, we love to build these beautiful mathematical models. We use them for everything, right? From figuring out how a virus spreads to watching the intricate dance of proteins inside a single cell. But there's always this huge challenge. How do we make sure our clean, perfect models actually match the messy, complicated real world? Well, that whole process of bridging the gap, that's called parameter estimation. And it's absolutely crucial if we want to build models we can actually trust.
And this right here is the problem in a nutshell. On the left, you've got our model's prediction. It's this perfect, smooth, idealized curve. Then you look at the right, and that's reality. That's our experimental data. It's noisy, it's sparse, we've got gaps, it's messy. So the whole goal, the entire point of parameter estimation is to find the right settings, the right parameters for our model so that its clean prediction can accurately explain this beautiful mess.
All right, so here's the game plan for how we're going to tackle this. First, we'll dig into that model data mismatch. Then, we'll do a really important checkup to see if our parameters can even be identified in the first place. After that, we'll learn how to find the parameters that matter most, and then dive into a powerful Bayesian framework to estimate them. We'll even look at a super clever workaround for when the math gets, well, impossible. And finally, we'll see why all this hard work is totally worth it.
Okay, so first things first, let's dive into that gap. Why don't our models and our data just line up perfectly right from the get-go? Well, it's because reality is swimming in uncertainty, and we have to account for it.
And really, this uncertainty is coming at us from all angles. Our measurement tools have noise. We can't collect data every single nanosecond, so our data is sparse, it's incomplete. Often, we can't even measure every single molecule in a system. Those are what we call latent or hidden variables. And on top of all that, biology itself is just fundamentally random or stochastic. So the whole point of parameter estimation is to find the model settings that best explain our data, despite all these sources of real-world messiness.
Now, before we get all excited and rush off to fit our model, we have to stop and ask a really, really important question. Can we even find a unique answer for our parameters? This whole idea is called identifiability, and trust me, it's a checkup you absolutely cannot skip.
So first up, we've got something called structural identifiability. Think of this as a purely mathematical checkup on your model's equations. It's a thought experiment, really. You ask, if I had perfect utopian data, no noise, no gaps, just flawless information, could I, in theory, nail down a single unique value for each parameter? This has nothing to do with your actual data yet. It's all about the fundamental structure of the model itself.
And then you contrast that with practical identifiability. This is where the rubber meets the road. This asks, okay, given the real, messy, sparse data we actually have, how well can we pin down a parameter's value? This is so important because a parameter might be perfectly identifiable in theory, but if your data is poor, it can become practically impossible to find. And yeah, it's not just a simple yes or no. There are actually levels to this. A parameter is globally identifiable if there's one and only one possible value that can explain the data. It's locally identifiable if maybe a few different values could all work. And it's not identifiable if a whole range, literally infinitely many values, all give you the exact same result. Our goal, of course, is to work with globally identifiable parameters. Otherwise, we're just chasing ghosts. Okay, so let's say we've confirmed our parameters are identifiable. Great. But, biological models can have dozens, sometimes hundreds of parameters. We can't possibly estimate them all with the same level of focus, so we need to be smart about it. That's where sensitivity analysis comes in. It's a way to find the parameters that are the real heavy hitters.
And the tool for the job is global sensitivity analysis. It's a really powerful technique that lets us figure out which parameters are the big levers in our model. It basically asks a simple question. If we wiggle each parameter around a bit, which ones cause the biggest swings in the model's output?
And you've got a couple of tools in your toolbox for this. The Morris method, for instance, is a quick and dirty way to get a general ranking of which parameters have the most influence. But if you want a deeper, more quantitative insight, you can use the Sobel method. It's amazing. It literally breaks down the model's output variation and tells you exactly what percentage is caused by each individual parameter and what percentage comes from its interactions with others. And boom, this is what you get. A Sobel analysis spits out a chart just like this. And right away, it's crystal clear. Parameters K2 and K4 are the dominant players, responsible for 65% and 25% of what's going on. All the other parameters combined barely make a dent. So the takeaway is huge. We can now focus our precious time and computational power on nailing down K2 and K4, and maybe just fix the others to some reasonable values.
We've done our homework, we've identified our key parameters. All right, now it's time for the main event, actually estimating them. And we're going to do this using a modern, really powerful approach called a Bayesian framework.
Now, this is where we see a really fundamental shift in thinking. The classical, or frequentist way of doing things tries to find the one single best answer. But the Bayesian approach, it's different. It says, hey, maybe there isn't one single right answer. Instead, it tries to find a full probability distribution of all plausible values for a parameter. This gives us a much richer, more honest picture of the uncertainty we're dealing with.
And it all boils down to Bayes' rule, which is just a formal way of learning from data. Think of it like this. You start with a prior distribution. That's your initial belief, your best guess about the parameters before you've seen any data. Then comes the likelihood. This is the data talking. It measures how well any given parameter set explains the data you actually observed. And when you combine your prior belief with the evidence from the data, you get the posterior distribution, your new, updated, more informed belief.
I really like this quote because it just nails the concept. The data, working through the likelihood function, acts like a filter. It takes your initial beliefs, your prior, and it reweights everything. It gives more weight to parameter values that do a good job of explaining the data and less weight to the ones that don't. It's just a beautiful, logical way to update what you know.
But hold on, we're not done yet. Just because we have an answer, this posterior distribution, doesn't mean it's the right one. We have to check our work. This is done using something called posterior predictive checks. Basically, we take our new parameter distributions and we use them to simulate a bunch of brand new datasets. Then we compare those fake datasets to our original real data. If our model is any good, the simulated data should look statistically just like the real thing.
Okay, this Bayesian framework is fantastic. It's powerful, but it has an Achilles heel. It all depends on that likelihood function. For a lot of complex, realistic biological models, that function is mathematically intractable. You just can't write it down. So what do you do then?
This is the million-dollar question, and it leads us to a whole class of incredibly clever methods called likelihood-free inference. And probably the most popular of these is something called approximate Bayesian computation, or just ABC for short.
The idea behind ABC is actually pretty simple, but it's also kind of brilliant. Instead of trying to calculate a complicated likelihood, we just simulate things. Here's how it works. You grab a parameter set from your prior guess. You use it to simulate a fake data set. Then you compare your fake data to your real data. If they're close enough, if the distance between them is less than some small number you decide on, you keep that parameter set. If not, you throw it away. And you just do this over and over and over again, maybe millions of times. And that pile of parameter sets you kept, that's your approximate posterior distribution.
So, the power of ABC is that you can throw it at almost any model you can simulate, which is amazing. But what's the catch? Well, it's a brute force approach. To get a decent result, you might need to run tens of millions of simulations. It can be a massive computational lift. It's a classic trade-off, really, between statistical convenience and raw computational horsepower.
So, wow. We've gone through this whole rigorous workflow, right? We've checked for identifiability, we've ranked our parameters with sensitivity analysis, we've used these powerful Bayesian tools to estimate them. So what's the big payoff? What do we get for all this hard work?
And the payoff for all that work, it's huge. Now you have a calibrated model that you can actually trust. You can use it for robust model selection, to quantitatively compare different hypotheses about how a system works. You can handle incomplete knowledge, building these cool hybrid models that combine what you know with a neural network that learns the parts you don't. And maybe the most powerful thing of all, you can use your model for optimal experimental design, to simulate future experiments and figure out exactly which one will give you the most bang for your buck and best shrink the uncertainty in your parameters.
So at the end of the day, what's this all about? It's about trust. Because our mathematical models of biology are only ever as good, only ever as reliable as the parameters we put into them. And when we finally have a rigorous framework to make sure those parameters are trustworthy, it just blows the doors open for asking and actually answering much deeper, much more exciting biological questions.